Now in our previous lectures, we have already seen linear differential equation. Now in today's lecture, we will move on to the next topic. It is called as linear differential equation with constant coefficients, or it is also called as higher order differential equation. Now, in previous chapter, what we have seen was first order, first degree differential equation. When I say first order, it means dy by dx. Only one time derivative will come. First degree, the power of dy by dx will also be 1. So that is called as first order and first degree differential equation. Now in today's lecture, we will be finding solutions to differential equations whose power, whose order is more than 1. I said power as well as order. For instance, if I write a differential equation, let us say d2y by dx square plus 3 dy by dx plus 2y is equal to, so if you observe this left hand side, in this d2y by dx square is a second order differential coefficient. dy by dx obviously first order differential coefficient equal to plus 2y equal to you get some function of x, anything. What this function of x is, we will see in little later. But then there will be some function of x in the right hand side. So left hand side is d2y by dx square plus 3 dy by dx plus 2y. This is a differential equation of order 2. Degree is 1. The highest order differential coefficient is d2y by dx square. Its degree is 1. So in this chapter, you need to find solutions to differential equations when the order is not 1, for higher orders and for higher degree. Now how do I get the solution? Now in this particular chapter, you want to remember, to get the solution, there are two parts that you need to find. Our today's lecture will be entirely focused on the first part. Solution will contain two parts. The first part is called as a complementary function. It is called as a complementary function. We write CF. So henceforth, whenever I say CF, it stands for complementary function. And the second part of the solution will be called as a particular integral. So today I am not going to go into the depth of particular integral, that is left for the next lecture. Today we will see only finding the complementary function. So particular integral is the second part. The short form is PI. So whenever I say PI, it stands for the particular integral of the solution. So we have a linear differential equation. Now when I say linear differential equation, again and again I am using linear differential equation. Further, the name of the chapter is linear differential equation with constant coefficients. Now why it is called as a linear differential equation? If you observe, I have already written one differential equation on the board. This one. It goes like this. P naught is a constant. It is a coefficient of nth order derivative dny upon dx raised to n. Then P1 is a constant. It is a coefficient of the n minus 1th order derivative d raised to n minus 1 by upon dx raised to n minus 1, and so on. So if you observe, all the differential coefficients are accompanied with some constants. That is why we say constant coefficients. Further, if you observe, the differential coefficients whichever are involved, even though they are of higher order, this is a higher order differential coefficient, but the power is still 1. The power, the degree of the differential equation is still maintained 1, but it is a higher order differential coefficient. So I hope you should remember the difference between an order and the degree of a differential equation. When I say order, it means how many times you are differentiating a differential equation. And when I say degree, it means the power of the differential coefficient. So order is nothing but how many times you are differentiating the equation, and degree is nothing but the power of the differential coefficient. So order and degree, if this difference is clear, we can now move on to what is a linear differential equation. So when I say linear differential equation, that means the power of the differential coefficient, the power I say, not the order. Power is 1, order can be anything. It can be n, it can be n minus 1, n minus 2, and so on. So the entire left hand side is a differential equation of order n and degree 1, that is why linear. Degree is 1, that's why linear differential equation. every differential coefficient is accompanied with a constant. That is why linear differential equation with constant coefficients, and hence it is also named as a higher order differential equation. So higher order means order of the differential equation is more than 1. Then, as I said, solution will contain two parts, complementary function and particular integral. What is particular integral? We will be looking into that matter a little later. So today, let's find out what is a complementary function. Now, to get the complementary function of the higher order differential equation, what next thing you need to know is d by dx. We write it capital D. D by dx we already know, it is written as capital D. Now d by dx, or if you write dy by dx, so I can write dy here. It is also denoted by y1. So y1 dy by dx, dy. Y2 can be written as d2y by dx square and d square y. Then y3 can be written as d3y by dx cube and d cube y, and so on. I can get yn, which is the nth order derivative, dx raised to n is equal to d raised to n y. So a linear differential equation will sometimes contain y1, y2, y3 and so on. The linear differential equation might sometimes contain dy by dx, d2y by dx square and so on. Or the linear differential equation might also sometimes contain dy, d square y, d cube y and so on. So this is called as a linear differential equation of order n. Order is n. How many times you are differentiating the differential equation? That denotes the order of the differential equation. Now, once I know this particular structure, the next thing that I need to know is how to get the complementary function. Now, people, to get the complementary function, there are few types that you want to know. The first type, the most easiest one, is, see, now basically what you need to do is you have to get roots. I want to get roots of the differential equation. Now what are roots? How do I get them? Observe carefully. The first one is when the roots are real and distinct. Now what is this complementary function? What is a particular integral? Let us not go into that much depth at this moment. It will be taken in the next lectures. So right now today our main concern is to just understand how to get the complementary function. So as I said, there are few types that you want to remember, of which the first type is when the roots of the differential equation are real and distinct. You can take the same example. Here it is d2y by dx square plus 3dy by dx plus 2y equal to some function of x. Now before I go to find the complementary function, there is some other thing that you want to remember, and that is called as an associated, or sometimes it is called as an auxiliary equation. Short form is A. So in the entire chapter we are going to make use of short forms. CF stands for complementary function, PS stands for the particular integral, and AE stands for either the associated equation or it is called as an auxiliary equation. Now, as I said, if I have a differential equation, I have taken this example. So this d2y by dx square, dy by dx and so on, I can write as dy, d square y. So therefore my differential equation, this one, the example that is given to you, will become d square y plus 3dy plus 2y is equal to some function of x. The capital letter denotes the function of x. You can take out y common from here. So I get d square plus 3d plus 2y is equal to x. So what is your auxiliary equation? Observe carefully. If you observe this bracket, this is entirely a function of d. Then there is a y is equal to something in x. So then auxiliary equation or the associated equation is nothing but f of d equal to 0. So whenever you want to find the complementary function, before I get the complementary function, who comes is the auxiliary equation or the associated equation. Who is the associated equation? It is nothing but a function of d. What is function of d? In left hand side, all the terms of d are taken together and y is taken out common. So this entire function of d is f of d. And when it is equated with 0, that gives me the auxiliary equation. So in this case, I have d square plus 3d plus 2 equal to 0. So that's my equation. D square plus 3D plus 2 equal to 0. That's an auxiliary equation. If you observe, this auxiliary equation is a second degree equation. It's a quadratic equation. And you all know we can definitely get roots of a quadratic equation. Is that it? So if you observe this quadratic equation here, the roots are very simple. If you take 2, the factors are 2 into 1. Now this is very important thing you want to remember. In mathematics, calculators are not allowed. So as much as possible, make sure to factorize the given equations by using some basic concepts of mathematics. And do not make use of the calculators. Even though calculators will definitely give us correct answers, but then it is expected that you should be knowing basic rules of getting the roots of the equation. So as I said, 2 can be factorized as 2 into 1, and this 3D can definitely be written as 2D plus D. So in our lower standards, we have seen how to factorize the equations. So at this moment, we need not show each and every step. We can directly write the factors. So it's D plus 2 and D plus 1 equal to 0. Therefore I get D is equal to minus 1, or I can say D is equal to minus 2. Who comes first, who comes second, it is irrelevant. It does not matter whatever the order you are going to maintain. Whatever order you want to maintain, you can keep that order. I have written minus 1 at the beginning and then minus 2. Usually what order I follow is, I always ascend the values. I always write the lower value at the beginning and then I keep on ascending the value. So for me, minus 1 was lower and then minus 2 and so on. It will keep on going further. So D equal to minus 1, D equal to minus 2, these are the roots. If you observe, these roots are real and they are distinct. Minus 1 and minus 2, they are different. So real and distinct. So whenever you get real and distinct, the first type of the complementary function. If the roots are real and distinct, see how do I write the complementary function. So CF is given as, it is given as y is equal to, or sometimes we write yc, because as I said, the solution will contain two parts. One from the complementary function, one from the particular integral. So from the complementary function, whatever solution part I'm going to get, I'm going to denote it by yc, and from the particular integral part, whatever part of the solution I'm going to get, I'm going to denote it by yp. So I'm going to represent it as yp, and this I'm going to represent as yc. So yc is equal to. Now observe carefully. This is what you want to learn. When the roots are real and distinct, I have two roots, minus 1 and minus 2. That signifies that there are two constants which are going to come, and it can be written as c1. The first value is minus 1, so I write e raised to minus x, plus c2, the next constant, and then there is minus 2, so I write e raised to minus 2x. That's how I get the complementary function for the given differential equation. Now this was an auxiliary equation. I have taken d square, but there can be an auxiliary equation where it can be d cube or d raised to 4 and so on. We will definitely take some examples on higher powers also. This was a very simple term that I have taken, simple equation, to let you understand how to take roots, how to get the roots and how to write the complementary function. So people, I can generalize this, and I'm going to generalize it in this way. Observe. Here I have got two roots. I have got two roots because I have considered a second order equation, second degree equation. It was d square, that is why two roots have come. If it was a cubic equation, definitely I'll get how many roots? 3 roots. If it's a power 4 equation, definitely I'll get how many roots? 4 roots, and so on. So whatever the power of the equation, that will decide how many roots you are going to get. So let us say I have a differential equation whose order is n. Let us take the order of the differential equation as n. Here it was 2. Since the order is 2, or I can say since the quadratic equation is obtained, I got 2 roots. If I get a cubic equation, I will get 3 roots. If I get a quartic, that means power 4 equation, I will get 4 roots, and so on. So what I am doing here is, I am taking a differential equation whose power is n. If I have a differential equation of order n, quadratic gave me 2 roots, cubic will give me 3 roots, power 4 will give me 4 roots, then power n will give me n roots. Further, if you observe, these roots are distinct, they are different from each other. So sometimes I might get a cubic equation, but I may still get different roots, distinct roots. If I take a power 4 equation, still I might end up with different roots. For instance, I can write like this: d plus 1 into d plus 2 into d minus 3 into d plus 4 equal to 0. If you observe, this is definitely going to be a power 4 equation, and all the roots are different. It is minus 1, minus 2. Roots are minus 1, minus 2, 3 and minus 4. Factors are d plus 1, d plus 2, d minus 3, d plus 4. So you need to know what is the difference between a factor and the root. So root is minus 1, minus 2, 3 and minus 4. What I did, I equated this factor with 0. So d plus 1 equal to 0, you get d equal to minus 1. D plus 2 equal to 0, you get d equal to minus 2. So that's how the difference between a root and a factor should always be remembered. So as I said, I have taken a differential equation whose order was n. I have taken a second degree equation, order was 2, power is 2. I've got two values of d. Hence my complementary function contained two constants. Here I am telling that it's a differential equation of order n. Let the roots are m1, m2, m3, m4 and so on till mn. So n number of roots have come. All these roots are distinct. So differential equation of order n, m1, m2, m3, m4 up to mn are n number of distinct roots. Distinct roots of the equation. They are distinct roots. So complementary function is given as, observe carefully. So I had the first value as m1. So m1 will go into the power of the exponential term, e raised to m1x. And since it's the first constant or the first root, I write c1. Then the second root is m2. So it will go to the power of the exponential, e raised to m2x. And it's a second root, hence I write second constant. Plus c3, e raised to m3x. And dot 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 till cn e raised to mnx. So that is how we write the complementary function. If the roots of the differential equation, or I can say the auxiliary equation, are distinct and real. So this is very important. It has to be real and distinct. I hope you have understood the first type. We will, in the proceeding lectures, we will definitely take the next types also. Note it down.